Hey, welcome everybody. So today we're going to be talking about the gas laws, and we should be able to understand the relationships between properties of gases. And by properties of gases, I'm talking about things like volume, temperature, pressure, and the number of moles of gas. So there are relationships between those properties, some directly proportional, some indirectly proportional, all of which can be calculated mathematically. So we're going to be going over that today. So the first one is Boyle's law. So Boyle's law relates changes in pressure and volume. And so this is one of the laws that is indirectly proportional. So as one of them goes up, the other one is going to go down. And the equation for this law is going to be P1 V1 equals P2 V2, okay? So here's an example problem. A 1.53 liter sample of sulfur dioxide gas is at 5.6 times 10 to the third pascals. So watch out for these pressure units. There can be several different pressure units. There are pascals, there are kilopascals, there are millimeters of mercury, there are torr, and I think the most common is atmospheres, ATM. Now in this case, we were given an initial pressure of 5.6 times 10 to the third pascals, okay? And we were also given an initial volume of 1.53 liters. So this is our starting volume, this is V1, this is our starting pressure, this is P1. It says to calculate the volume, so we're going to be calculating the new volume, V2, if the pressure changes to 1.5 times 10 to the fourth pascals. So this is our second pressure. This is P2. So I had pascals for the first pressure, I have pascals for the second pressure, which means I don't have to do any conversions here. Now if you're given an initial pressure in pascals, but you're given a new pressure in atmospheres, one of them is going to have to be converted. So within the same gas laws problem, you need to have the same units for volume, right? So if I have liters, I'm going to end with liters. And you have to have the same units for pressure. Since we have pascals for both measurements, that's fine. We don't have to do any conversions. So all I'm going to do here is once I've identified each variable, I'm just going to plug them into the problem. It's plug and chug. It's very simple math. So for P1, 5.6 times 10 to the third. For V1, it's going to be 1.53 liters. It's okay. And then I've got the second pressure. So that's going to be 1.5 times 10 to the fourth pascals. And then I'm looking to find the new volume. Okay? So again, once I've plugged this into the equation, I'm going to go ahead and multiply these two, and then I'm going to solve for V2. Okay? So if we multiply those two values, let me grab my calculator real quick. We get, let me put it in parentheses here, 5.6 times 10 to the power of 3, put that in parentheses, multiplied by 1.53 liters. Okay, so I have 8,568 on this side, is equal to 1.5 times 10 to the fourth V2. Again, so the math is pretty simple. After I've multiplied the side of the equation that has two numbers, I'm going to go ahead and divide by the other side. So that product, 8568, is going to be divided by 1.5 times 10 to the fourth power in order to solve for V2. And so I ended up with a value of 0.5712. Now if I look in the equation, the fewest number of significant figures that I have is 2, so I'm going to keep 2 sig figs in this problem. In this case, V2 is going to be 0.57 liters. Okay, now we have to ask ourselves, does this make sense? If I look at the pressure, it went from 10 to the third power to 10 to the fourth power, so it increased quite a bit. So if the pressure increased, and this is an indirectly proportional relationship, then the volume should decrease. If pressure goes up, volume should go down, and vice versa, if it's indirectly proportional. And so did my volume go down? Yes, it did. It started at 1.53, and now it's down to 0.57. So this answer definitely makes sense. Okay, so the next gas law up relates changes in temperature and volume. This is going to be a directly proportional relationship. And the temperature has to be in Kelvin. Now, I didn't mention that in the Boyle's law problem, because in Boyle's law, temperature doesn't matter. So temperature wasn't even mentioned in the first problem, or they might mention temperature but say that it stays constant. So if they say that the temperature stays constant, it doesn't matter. It's not a variable in the equation you need to use. However, if you do have changes in temperature, all temperature values have to be converted to Kelvin before you're able to plug them into the equation. How do you do that? Anytime you need Kelvin, Kelvin is equal to your degrees Celsius plus 273. The reason is we use the same scale as the Celsius scale, but the Kelvin scale is set so that there are no negative values. So you should never have negative Kelvin. 0 Kelvin is what we call absolute zero, and that's the temperature at which there's no kinetic energy. Because really what happens when things heat up is that their particles speed up. And so at 0 Kelvin, they're not moving. So there is no negative values in the Kelvin scale, which mathematically we want in these problems. We don't want any negative values. Anyway, the equation for Charles' law that relates temperature and volume is V1 divided by T1 is equal to V2 divided by T2. So you'll notice that the directly proportional gas laws are set up as proportions, which makes sense. Okay, so then on the back, we have this example problem. It says a gas has a volume of 2.58 liters at 15 degrees Celsius and 1 atmosphere. Calculate the volume at 38 degrees Celsius and 1 atmosphere. Now again, if I look at my pressure, all of a sudden they threw a pressure in here, but you'll notice that it didn't change. And like I was saying before, if it doesn't change, it doesn't matter. It's not going to be a variable in the equation. So really all we have is a volume and a temperature. They're asking us for a new volume at a new temperature. So the only things that are changing are volume and temperature, which is why Charles' law is appropriate to solve this problem. Before I do anything though, I need to do some conversions. That 15 degrees Celsius, I have to add 273, so this becomes 288 Kelvin, okay? Again, I would do the same thing for the 38 degrees Celsius, so 38 plus 273 is gonna be 311 Kelvin. So I need to make those conversions before I plug them into the equation. Now I go ahead and plug these in. So it's V1 divided by T1. So it's going to be 2.58 liters, because that was my starting volume, divided by 288 Kelvin is equal to, I don't know my second volume, but I do know that the second temperature is now 311 Kelvin. Now, before I even work out this problem, I can make an estimate about the answer. If my temperature is going up, my volume should go up. So whatever answer I get should be greater than 2.58 if I'm doing this correctly. When we are going to solve this problem mathematically, we're going to use cross multiplication and division. So we're going to multiply diagonally in whatever direction has two numbers. So it's going to be 2.58 times 311. And I get a product of 802.38. Then you divide by the number that's left out. So I'm going to take that and divide by 288. And so my answer, and since I have 3 significant figures and everything, my answer is going to be 2.79 liters, because that was the unit that I was given for volume. And so 2.79 is greater than 2.58, so that's a reasonable answer. Okay, the next one is going to be Avogadro's law. Avogadro's law relates changes in volume of gas and moles, so number of particles. Again, this is going to be a directly proportional relationship. So it's going to be V1 over N1 is equal to V2 over N2. So N is going to be your number of moles. So you should be given units of moles here in these problems. Now, if you're not given units of moles, you may be given mass, but mass can be converted to moles. So watch out for those kinds of problems. Again, you would set it up just like this, directly proportional. You would plug those numbers into those proportions, you cross multiply and divide. And so I don't have an example for you. I will say, watch out in the problems. Make sure you're using the appropriate equation. Again, they may mention volume, moles, and temperature, or they may mention volume, pressure, and moles. But if one of them stays constant, like we saw in this problem here, then don't include that in the equation that you're going to use. It would cancel itself out anyway. So it's not necessary to solve the problem. Just worry about the things that are changing and choose the equation that has those variables in it, okay? All right, Guy-Lussac's law is the, again, directly proportional relationship between pressure and temperature. Okay, and so pressure and temperature have this directly proportional relationship. When you increase the pressure of gas, you're going to increase the temperature. And likewise, when you release the pressure, when you decrease the pressure, it's going to decrease the temperature. Air conditioning systems and refrigeration systems use this quite a bit. That's why you have a condensing coil in the back of those different things, so that you can condense and then release the pressure in the gas and therefore change the temperature. Anyway, so it's going to be P1 over T1 is equal to P2 over T2. And again, make sure your temperature is always going to be in units of Kelvin, and make sure that your pressures are the same. So if one is atmospheres, the other has to be atmospheres. If one is millimeters mercury, the other has to be millimeters mercury. Now, the combined gas law is the one that you use if you do have changes in 3 or more variables, okay? Now, if any of those 4 variables is held constant, it can be removed from both sides of the equation. So let's say they change volume, temperature, and pressure, but they don't change the number of moles. Then we can simply remove moles from both sides of the equation, plug in the numbers we have, and solve. So the equation for the combined gas law is P1 times V1 over N1 times T1. So all of your initial values are equal to P2 times V2 over N2 times T2. Okay? All right, thanks, guys.